So today we finished the renormalization section, then we can move on to QED. There are three types of renormalizations. That one we typically talk about. One is coupling constants. And that's the one we've done. So that's you renormalize lambda, or you renormalize the electric charge, etc. And here you pick a scattering amplitude, you calculate away, you identify your renormalized parameter. The next is mass renormalization. It's basically the same. I mean, a mass is, in a way, is a parameter in a Lagrangian. A coupling constant is a parameter in the Lagrangian. The only difference is you do a different diagram for this one. Okay? And the third one, which we also do today, is wavefunction renormalization. Okay, that's a little bit more subtle. So, but it's also so it's a little bit more subtle, and we'll talk about that today too. Okay, so the place where we have these two still to do, the place where you do that, both of those gets done in what are called the self-energy diagrams. And the place we do that is the propagator. Okay. So when we have some place where we're using the propagator, you know, the propagator looks like I over p squared minus m squared plus I epsilon. There's a couple things in that. This is I over e squared minus m squared plus I epsilon. And if you remember the identity that we had before, we show that this is well, there's an I out in front, but there's a principal value of 1 over, I'm sorry, I went too fast here. E squared minus p vector squared minus m squared. So it's principal value of e squared minus p vector squared minus m squared. And it's minus I pi delta function e squared minus p squared minus m squared. So there's two pieces here. One piece you might think of as off shell. In other words, you've deliberately cut out, when you do the principal value, you deliberately cut out the region where that goes to 0. And this is the piece that's on shell, where it defines the energy and momentum relationship. So if we're interested in the mass, we're interested in that piece, which in turn we're interested in the propagator. Okay? So the trick is that interactions can shift us. So let's imagine you're doing some case where you have some propagator. So there's some stuff going on up here. Here's your propagator and some stuff going on down there. And you have some interaction. So stuff up above, propagator. Well, there could be some, if you're doing a charged particle, you could have a photon that goes around like that. So there's a photon. Or if you're doing the type of theory that we're doing, lambda phi to the fourth, there's an interaction that looks like that. There's a loop there. These guys, this type of diagrams, are what we call the self-energies. So it's called minus I sigma of P, that's the self-energy, and it's defined by the Feynman diagrams that look like that, or look like that. The only thing I would comment is that you drop any external factors. So in other words, if there was a U bar U, you drop the U bar U. Okay. So in general then, if you take the full propagator, okay, you would take this picture plus this picture plus this picture plus this, etc. And then there's also corrections. There actually are higher order corrections. There are things that, here's a two-loop correction, etc. And so you'd have two loops there and one loop there, etc. Okay. So anything that starts on one particle, ends on one particle, it goes into the propagator. And so if you count all the things that look like that, all the things like that, we call that the self-energy. This propagator starts like I over P squared minus, let's call it M0 squared plus I epsilon, just to keep, that's the bare parameter in the Lagrangian, plus I over P squared minus M0 squared plus I epsilon minus I sigma of P. Then there's another I over P squared minus M0 squared plus I epsilon. Okay, so if I put this diagram in a vertex, that first one would have been just the propagator, this one would have been propagator, sigma, propagator. Here's, now the next one I'll write out is sigma squared. So then the next one is I over P squared minus M0 squared plus I epsilon minus I sigma I minus I sigma again, and then another one. Okay, so clearly we keep going dot dot dot. It's a geometric series. It sums to I over P squared minus M0 squared minus sigma of P plus I epsilon. Okay. So now this shifts the on-shell condition. Then now that pole in that propagator, P squared minus M0 squared minus sigma of P equals 0. Okay. In perturbation theory, this is relatively easy to solve. I mean, in general, that could be a nonlinear equation. You know, sigma can have some complicated momentum dependence. But in perturbation theory, it's not too terrible to solve. In perturbation theory, you treat that as a perturbation. We write sigma of P squared as sigma of M squared plus P squared minus M squared sigma prime of M squared. So we're Taylor series expanding it around some point. Okay. Now, this is not technically, it's not M0. It's going to be the physical mass. We then have m squared is m0 squared plus sigma of m squared. And that's the physical mass. Okay. Now, so it's not that hard. In perturbation theory, it doesn't make that much difference if you used M0 or M physical here, because this is already of order alpha, or there's some coupling constant. Some coupling constant shifts this. So this is something without the coupling constant plus 1 times the coupling constant. And that's an easy thing to solve then. And so then you go back and you make this expansion around that point. So it's a little bit iterative. Okay, so that's where the pole occurs. Okay. So that's going to be mass renormalization. We're going to identify the physical mass, not as this bare mass, parameter in Lagrangian, but this shifted one. The wave function renormalization is the next term there. Okay. Let's keep the next term in this expansion. So I've got 1 over p squared minus m0 squared minus sigma of m squared minus p squared minus m squared sigma prime of m squared. Okay. So now if we've identified m squared as this combination, then both these terms have p squareds minus m squareds in them. So this looks like I over p squared minus m squared 1 minus sigma prime of m squared, which we write as z p squared minus m squared. Okay. So we see that the next term has the feature of shifting the magnitude of the propagator. Okay, that's the problem. The logic of wave function renormalization goes back to things that we did early on. Remember, we defined the propagator as 0 time-ordered product of phi at x and phi at y, 0. So that, and we went through a little calculation that said that del box plus m squared, del squared plus m squared, IDF is, well, if you worked out that it turned into the commutator of phi of x, so if this is with respect to y, d0 phi of y at x0 equals to y0. So there was a theta function that we differentiated. Times, so there's delta of x0 minus y0. And this was I delta 4. Okay? That's the whole calculation that we did. This was our commutation rule that defined the theory. And we see that if you go back and plug this propagator back in, you have to have it absolutely normalized, so there can't be any factors. So if I had plugged that propagator back in, of course I missed by a factor of z. And so it's the commutation rules that's the defining property. And it tells us that we've screwed up the normalization now by doing this. The screwing up the normalization comes from that term in the self-energies, and so we need to readjust the normalization. Okay. So if I define phi of r is z to the 1/2 of phi, that's my starting phi. This is now the renormalized field. Phi of r then will have the correct propagator. Okay. Now, this isn't something that's special to field theory. This happens even in quantum mechanics. So let's do quantum mechanics. Just to show you. If you're doing perturbation theory, you write that some wave function starts off whatever the wave function started off as, and then the first order correction to the wave function is psi j0 psi j0 v psi I0 over EI minus EJ. And if you just do that, then it's clear that if this originally was normalized, this is going to screw up the normalization. So what you have to do is you always have to renormalize this whole bloody mess. There's some renormalization, which is really the same effect as our z to the 1/2. And the way you would calculate it is just by squaring the diagram. So if you were taking psi I, this might be represented by the first term just being a line, and the second term, if you have an interaction, might be something that looks like that, where there I've gone into some intermediate states. So if this is an electron, a gamma electron, is the square of that term. So it's really the same thing. So you also need to do exactly the same thing in quantum mechanics, but the technique is slightly different. Is that here we go through the propagator. Okay. So that's the definition of these two guys. So we have mass renormalization and wave function renormalization. I'll go through the general techniques of them too, but let me just again do some logic on this. We end up dropping the mass renormalization. I'll give you the formal techniques of that in a minute, but first let's just think about it. So if you recall back when we did phi to the 4th scattering, we took that diagram, we took that diagram, and there's one that looks like this. And we found diagrams that look like that, but we dropped them. Okay. And so first, why did we drop it? Well, the logic is that any time you have some process, so let's imagine I'm doing this scattering process. There's somewhere back in the distant past, there's some place where you produce the phi, and then it comes along and it scatters off another phi, and it scatters. Okay, so you put it in an accelerator, you send it down the beam track. That process includes all these diagrams. Okay, so that in producing it, the net effect of all these diagrams just produces the physical mass. Okay, now that's actually not quite true. If you were to do this calculation, let's imagine this is vertex number 1, this is vertex number 2, then the piece that corresponds to that process then would be the on-shell part. And we would have had vertex 1, whatever it is. We would have had the minus I pi delta function of p squared minus m physical squared. We would have had this factor of z, and then you would have had vertex 2. So the point is that this factor, it's not enough just to do the factor of going to the physical point. There's also some effect of z. And so when I do the technical part, you'll have to follow that also. So it's not enough to just drop them. You have to plug in z's in various places. Okay. So let's do the formal technique. I'm going to do this in 2 steps. I'm going to do mass renormalization by itself. So first I just do mass renormalization. Then I'm going to come back and I'll do everything all at once. I'll do mass renormalization, coupling constant, and wave function all at the same time, because that's what you really have to do. It's notationally complex when you do that. And so I want to do the easy one first. Okay. So this is the counter-term method. Okay. So we imagine starting off with a Lagrangian as 1/2 d mu phi squared minus m0 squared. That's the piece I'm focusing on. Minus lambda over 4, phi to the 4th. And that parameter there is the bare mass. That's not yet had the quantum corrections. But now I express it in terms of the physical mass. Okay, I don't yet know what it is, but let's just do it. It's whatever I've measured in the lab. Minus m squared over 2 phi squared minus lambda over 4 phi to the fourth. But then that I've changed it, so I have to, there's the extra piece here. Let's write it as plus delta m squared over 2 phi squared, where that's m squared minus m0 squared. Okay, that's the shift. Okay, I now treat this as a perturbation. So there's a new Feynman rule. Which, if I draw it by a little x, that's my counter term, is I delta m squared. So now in all diagrams I have to put this little x. Okay? So now we go off and calculate. We're now calculating with the physical mass. And we do all the usual stuff. So minus I m is this guy plus that guy plus dot dot dot. Then you come to this self-energy diagram. So there's this. And then there's a new one, which is, put the little x there. We also calculate the propagator minus I sigma of p squared it's this plus this plus this now. Yes? This guy. That's right. So phi, and then x. So that's. Why these guys? So in this case, I'm doing phi scattering. So I want to have 2 phi's in, 2 phi's out, and that's one way. This is another way. Here's another way where you have this interaction along the pathway. And then here, there's also another thing with this new Feynman rule. So, okay. Well, so maybe I should have written this one down first. Here's this propagator. What we're going to do is we're going to choose in the propagator, since this guy has the physical mass in it already, we want to choose delta m such that the sum of these two gives 0. Okay? Then the sum of these two are going to give 0, and that's the reason why we drop them. Okay? But the reason we now have this new perturbation here that takes one particle to one particle. So it's not only this diagram, there's also a bunch more here where these other legs get also the same treatment. So maybe I need to write that out there. Plus one that looks like this. Okay. This x here, I don't know if you want me to draw a little box around it. Those aren't external states. Those are just, that's just this new Feynman rule.
Also like
yeah, so it's going to cancel the self-energy term. We'll see that this will be identified as the sigma of m squared. Okay. So let's do it now, and then we can come back to your question if you want. So let's look at the propagator. So we have this I over p squared minus m physical squared plus I epsilon plus this guy minus I sigma, and then this guy is I over p squared minus m squared I delta m. Okay, this sums up then, plus, you do all the higher order terms. Also, again, the geometric series sums up to I over p squared minus m squared minus sigma of p plus delta m squared, delta m squared, sorry, plus I epsilon. Okay. But now, this is already the physical mass. And so, if that's the case, then we identify delta m squared is sigma of m squared, so that those guys sum up to 0. Okay, so now my propagator is the right propagator, is the right pole in the right place, and I've got and that should be sigma of m squared. Sorry. Okay, so sigma of m squared is identified there. And then now my propagator is right. And now all these terms cancel. So the result of this is then all predictions use the physical math and you drop external self-energies. Okay. Okay, so that's the logic. Anyone? Questions about it? You can see that if I had, so here I just did the self-energy. I didn't do the wavefunction renormalization piece, which would have been what I'd have to do if I keep the next term in this expansion. Okay. And that then leads to some changes. And so I'll do that now, but I'll do the same procedure, but I'm going to do everything all at once. Okay. Okay, so general case. Okay, here it's a little bit more complicated, but the logic is the same, so we've gone through the logic. We start with a Lagrangian that has 1/2 d mu phi squared minus m0 squared phi squared over 2. Now, I'm going to do coupling constant renormalization here too, so there's lambda over 4. But we know that this guy has, if you just proceed with it, has the wrong mass, the wrong coupling constant, the wrong normalization. So step 1 in this is wavefunction renormalization. So we're going to take phi r is defined to be z phi, let's call it z phi here, minus a half phi, or phi is phi renormalized. Okay, it's not yet known. So at this stage we have then the Lagrangian is z phi in the kinetic energy piece minus m0 squared z phi minus lambda z phi squared and those are the renormalized fields. In the end, they have to be chosen to be the properly renormalized fields. Okay. Step 2 is use the correct mass and coupling constant. Okay. This will then lead to counterterms. So at this stage, we don't yet have any counterterms. Well, actually, we could have. Okay. So we're going to write this then as L is 1/2 d mu phi renormalized squared minus m physical squared, that's whatever the physical mass is, minus lambda physical over 4, phi to the 4th, plus the counterterm Lagrangian. So let's write LCT. Okay, and now it's a bunch of, it's just a little bit of algebra. L counterterm, which is going to be our perturbation, is then going to be, well, let's give it names. It'll be delta z d mu phi r squared minus I want delta m squared over 2. It's plus delta m squared over 2, actually, given my previous notation. And minus delta lambda over 4 phi. Okay. So then step 3 is the counterterms as perturbations. Okay, so here's the perturbation. There's that little guy that I had before, but now it has two pieces. It's I delta m plus delta z p squared minus m squared. And then there's a counterterm that looks like that. Is minus 6i delta lambda. Okay? Yes?
Why didn't we drop the z phi from the first line to the second?
Well, I didn't. I did. Why did I? So here, delta z is equal to z phi minus 1. Okay? So I should say that. So if you go back, you look up here, there's a z phi. I broke it up into something with the right, with 1, and then something that is the difference. Okay? And so that's why there's now a delta z sitting down here, because I've shifted delta z into there. Okay. So now, treating the basic Lagrangian as the usual one, I have all my usual Feynman rules with all the right masses, the right normalizations, everything. Okay. So then you renormalize the propagator. Okay, minus I sigma. Oh, I've already got that there. I've already written that up there. So the full propagator, let's, I don't know, draw it nice and heavy. Oh, this has an erase function where if you scribble on it, it erases. There, so there it's nice and heavy. Let's go in. Okay, is equal to the basic propagator plus the whatever your Feynman rules are plus the counter terms plus dot dot dot. This sums up to I over p squared minus m physical squared minus sigma of p, and then plus delta m squared plus delta z p squared minus m squared. Okay. If we write this now as sigma is as before, sigma of m squared plus p squared minus m squared of sigma prime at m squared plus dot dot dot. Okay, so the thing I'm dropping is the order p squared minus m squared squared. Then the propagator has the right mass and normalization if I choose delta m squared is sigma of m squared and delta z, which is z phi minus 1, is sigma prime of m squared. Okay. Which, remember, is the way one can get that is that's the derivative with respect to p squared of sigma of p squared evaluated at p squared equals m squared. Okay, so that's the, you most often see it written that way rather than with the prime, but okay. Okay, so now I've got my mass renormalization, my wave function renormalization, and actually, and now the coupling constant renormalization. What am I up to? I'm up to 5. Okay, delta lambda. Let me actually just write it out. Actually, I should have written out delta m. It actually was z m squared minus m0 squared. No, in perturbation theory, the first order, which is the order you're working, this is already of order your perturbation, so this can be taken to be 1. But if you're doing higher orders, if you were to do higher orders, then you'd have to take into account that factor of z there. In delta lambda was, just algebraically, was lambda 0 z squared minus lambda physical. Okay, and this z squared there is now new. Okay, so last time I did, and this z is z phi. Last time I did coupling constant renormalization, I didn't do wave function renormalization at the same stage. But the procedure is the same. You take minus I m at some renormalization point, which is then this plus these diagrams, all these diagrams, plus, well, let me just put dot, dot, dot rather than keep drawing them. But then there's a delta lambda piece. And this is defined as minus 6I lambda at that renormalization point. Lambda r. Okay. And that identifies delta lambda. Okay. And at this stage, you just go ahead and calculate. Everything now comes out expressed in terms of the physical masses. And if you had to do yet another calculation in this theory, you know, let's say 2 phi's going to 4 phi's in the final state, this procedure would lead to finite results there also. Okay. Okay, so that's the procedure. Remember I said there are two procedures. What we just did here is this BPH, Bogoliubov Parizek Hep renormalization with counter terms. The other one is this direct or conventional okay. The other procedure is this conventional one where you work with M0, lambda 0, etc. The thing I have to say is that if you do this, there's actually a new Feynman rule been snuck in here. The wave function, the mass renormalization is the same, but there's a new now rule in this case where it's a new Feynman rule that says you do z phi to the 1/2 for each external state. Okay. Okay, and that you can see it up above here. You have to take your bare coupling constant, multiply it by z phi to the 1/2 times 4, which gives me that factor there. So it's lambda renormalized is lambda 0 z phi to the 4th plus some diagram stuff. So yeah, well, I'm just drawing these diagrams roughly. Okay, this goes into what we've called delta lambda above there. But this new rule has that feature there that accounts for what we did up above. It's, all right, so let me leave that. But if you end up doing this procedure, you have to take into account that. So if you do that, find a book that uses that procedure and just use the book as a guide. Okay, fair enough on that. Okay, so that's the technique. So what we've done is we've done the philosophy, the practicality, and then some of the practicalities of doing diagrams. The last thing that we have to say is talk about renormalizable versus non-renormalizable theories. Okay, so I'm going to put these in quotes because the terminology is actually lousy. And it's lousy for the wrong reason. It's not just a cute historical feature. It's that people didn't for a long time understand renormalization very well. And they just made the names, the fact that these names propagated for so long is a feature that people didn't understand what they were doing, really. And so let me start with the following statement. Any theory can be renormalized. There's a couple caveats on this, but it's in general a true statement. Okay, so I'll write caveats, and I'll tell you some caveats. But for the most part, in the sense of this division here, any theory can be renormalized. And what does that mean? Is that you can absorb the divergences into the parameters of Lagrangian and make physical predictions using measured parameters. Okay, that's the heart of renormalization. You take a theory, you calculate it away, you measure your parameters, you make predictions in terms of what you measured. Okay, and here's a caveat, the most important caveat here. Okay, and it goes by the phrase, whatever is not forbidden is required. Okay. It's the opposite of the old communism. Which, in communism, whatever is not required is forbidden. Here is whatever is not forbidden is required. And what that means is that you can't arbitrarily drop some term for no reason at all from the Lagrangian. So you can't drop terms without a reason. Okay, and here's an example. Let me imagine I wanted to write out a Lagrangian 1/2 d mu phi squared minus lambda over 4 phi to the 4th, but no mass term. Okay, that's a no-no. And that theory, if you tried to do that theory, you couldn't renormalize it because the lambda phi to the fourth generates a self-energy and requires that you need a mass term for renormalization. Okay. So you would have a divergence, that diagram, divergent. You wouldn't have any place to put it because you don't have a mass, so you don't have a delta m squared. So the only way that you can treat this theory in general is you write out all the terms that are plausible. You include the delta m squared piece, and then this divergence gets absorbed into delta m squared. Okay, the physical value of the mass. But as a counterexample to that, if I did the following theory, if I did same start, d mu phi squared minus lambda over 4 d mu phi squared. So this is forbidden. This is not good. Okay, so this guy actually is okay. It's actually not quite okay, but let me, as far as the mass, drop the mass. Okay. Now it seems a little funny. Here I've got lambda phi to the fourth, and all I've done is I've added some derivatives there. Right? Now anyone care to give me the reason there? I don't know if anyone can see it. It's a little subtle. Okay. That's okay because there's a symmetry here. If you take phi goes to phi plus a constant. The second theory has that symmetry, and m squared phi squared would violate that symmetry. Okay, so it's forbidden by a symmetry. So you can drop certain terms by forbidding them by a symmetry. This symmetry is called shift symmetry. You shift the field. And this is for example, this is a property of phonon interactions. For example, if you take, or let's do the waves on the string again. If you shift the whole string, if the phi was the height of the wave, and you shift the whole string by a constant, the theory is invariant. So this type of Lagrangian would be one that you'd have for phonons or for waves on strings, things like that. They'd be massless to all orders. Okay. Actually, in this case, you would actually have to do more, and that's part of what I have to explain. You'd also have to do terms that look like d mu phi. Oh, let's make it to the fourth power plus. Okay, you have to keep doing more terms like that, and I'll explain that part in just a minute. So all these theories can be renormalized. Okay, but they're not all renormalizable. Renormalizable in this sense is a separate classification. Which has nothing to do with being renormalizable, so it's terrible phrasing, and that's what people didn't understand. A renormalizable theory is one where infinities, if you're focused on infinities, can be absorbed in a small number of couplings. Or you might say sensitivity to high energy physics is there. So QED is renormalizable. You only have to renormalize the mass, the charge, and the wave functions. There's actually two wave function renormalizations. There's the fermions and the photons. Okay. Lambda phi to the fourth theory is renormalizable. There you have m lambda and z phi, and that's all. Okay. The criteria for this new classification is that all parameters in the Lagrangian are dimensionless or positive mass dimension. Okay, so dimensionless coupling constants are like E or lambda, those are dimensionless. Positive mass dimensions are things that look like m squared, phi squared, or m psi bar psi. So they have positive powers of the masses when you count things. So if we recall the counting of the various fields, okay, remember the dimension of phi is mass to the first power. If we go back and count, the Lagrangian is mass to the fourth, derivatives are mass to the first, the dimension, so this little square bracket is sometimes used for the dimension, goes like m to the 3/2. These also come from commutators. You know, the commutator of phi with d mu phi is delta function. The mass dimension of A is mass to the 1. Lagrangian goes like mass to the fourth, etc. So this then tells us that if you want positive mass dimensions or dimensionless, it tells you that the fields and derivatives have to be dimension, whatever the operator is in the Lagrangian, has to be dimension less than or equal to mass to the fourth. Okay? If it's equal to mass to the fourth, then the coupling constant that goes in front of it is dimensionless because the Lagrangian's dimensionless, the dimension mass to the fourth. If it's less than mass to the fourth from the operators like psi bar psi, then you have to put a mass in front of it to get the right, to get the Lagrangian have the right form. Okay, so the criteria can be phrased in terms of the coupling constants or the operators that are in the Lagrangian. Okay, so what is the distinction here? I mean, first of all, why does this happen? Well, if your coupling constants are dimensionless, then your expansion parameter goes like 1 plus lambda times with some number 1 over d minus 4. These carry the same dimensions, and so you don't generate any higher dimensional operators. Okay. And the proof is very complicated. I'm not going to do anything close to a proof, but that's really what the physics is. It's really just counting powers and using dimensional regularization, so there's no new powers been put into the game. And these things then don't generate divergences at higher and higher orders because they just multiply the same old pieces. So let me give you an example. Oh, good, I got it. Okay. The example and the counterexample. So non-renormalizable is anything else. So let's do the example of Lagrange. I'm going to have a renormalizable term and a non-renormalizable, and we'll see the difference. D mu phi squared minus m squared phi squared minus lambda over 4 phi to the fourth. Let's put in g6 over m squared d mu phi squared phi squared. Okay, and then I'm also going to add, just because I'm going to need it in a minute, g8 over m to the fourth d mu phi squared. Okay. So this first term is renormalizable. So in this classification, the second term, or these terms have inverse powers of the mass. So those are both so-called non-renormalizable. Okay. So now let's just do some loop processes. Okay. So let's do one loop diagrams. Okay. If I do, so this is if you remember this process starts out as minus 6i lambda, and then at next order there'll be something that looks like minus 6i lambda, some stuff that ends up being divergent as there'll be 1 over d minus 4 plus dot 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 6i lambda squared. Okay, so that's how the renormalizable piece goes. So if I do lambda and lambda there. Okay. So this basically then, you absorb that divergence into lambda. So this goes into minus 6i lambda renormalized. However, if I did it with the non-renormalizable interaction, and let's do the same thing now with this guy, g6 over m squared, g6 over m squared. There'll be now a term that looks like g6 G6 squared over m to the fourth, right? Because that's just the coupling constant. And there'll be some function of m squared, p squared, and p to the fourth. All right, let's make it that way. Okay. This overall has to be dimensionless. It starts off dimensionless, so the scattering amplitude is dimensionless. So this guy has to be dimensionless. So it's if it's m to the fourth downstairs, it has to be m to the fourth upstairs. M squared, p squared, p squared, p to the fourth. Now the trick on renormalizing it is this guy goes into renormalizes lambda. So there's just some shift in lambda. There'll be divergences also, so I can write 1 over d minus 4. This guy has the same form as this operator here does. It has a p squared sitting out in front, and it leads to 5-5 scattering. So that would renormalize G6. So that's fine. This guy, p to the fourth, has 4 factors of the momentum. Looks like G8 there. So this would renormalize G8. Okay. Now, so there's my first statement, is that these can be renormalized. Okay, so I've renormalized the theory now. Let's imagine I've done the calculation. You can renormalize the theory, but what I've had to do now is I've had to I now have to renormalize a new guy. So at one loop using this, I have to renormalize G8. That goes like, something like G6 squared over d minus 4. And at 2 loops, I'll have to renormalize yet other operators. I'd have to renormalize, G10 and G12, etc. You have to keep doing it. So you have to keep doing more and more operators. Okay. So non-renormalizable theories like this one, you have to do a continuing set of renormalization that leads to more and more operators and becomes less and less predictive, because now I have to measure these new coupling constants there. And so something that in another theory might have been predicted, in lambda 5/4 might have been predicted, like the momentum dependence, is now no longer as predictive. I have that example worked out, but I think I'm going to have to skip it for time reasons unless you want to see it. But if you look at the scattering amplitude, you can see that the momentum dependence of one loop from this and this at tree level bear some resemblance, and so you've lost a little predictive power because you have to go out and measure a new parameter. So non-renormalizable interactions are less good because they're less predictive, but not because they can't be renormalized. Yes, possible. Oh, that was stretchy. Okay. So I'm going to stop it there. There's unfortunately so much more left to be done in renormalization theories of theories, but I think it's probably best logically to stop at this stage and then come back to it later on in your career when you actually have to do something and it becomes less of an abstract concept and more of a practicality. We're going to go off to QED. I'll show you how you renormalize QED and make real predictions there. That's the next step. Okay? Good.